Interpretations of the derivative. So now that we've spent a bit of time talking about how we compute the derivative, it's really important that we understand the inner workings of what's happening on a small scale when we approximate. Additionally, we need to make sure we understand what the units of the derivative are when we're calculating such things. So far in this course, we've used what's called Newtonian notation. So that's because it came from Sir Isaac Newton. So that notation is what we've been using that looks like the f prime of x. When we use that prime mark, that came from Newton, and that's what we mostly use because the shorthand's a bit easier. However, while Newton was developing calculus, Leibnitz was also developing calculus, and Leibnitz used a slightly different notation. He used the notation dy dx. Now, dy dx represents the derivative of y with respect to x. So in that shorthand notation, y is our dependent variable and x is our independent variable. So what happened was Leibniz took the general formula y equals f of x and he said, okay, what if I take the derivative with respect to x of y? And hence we get dy dx to also represent that we're taking the derivative. Now, we can use these notations interchangeably. Generally, you will see Newtonian notation, but when we talk about things like units, sometimes it's really helpful to look at how Leibniz wrote out the derivative to understand where the units were coming from. This also matches up with what we know about average rates of change. So when we talked about average rates of change to get to the instantaneous rate of change, we were looking at the ratio of two things. We had something over something, and that also helps us understand where the units come from. So remember, when we talk about dy dx, we're talking about small differences in the y values over small differences in the x values to approximate the derivative. So ultimately, when we talk about the units of the derivative function, it's going to be the units of the dependent variable divided by the units of the independent variable. And that matches up with Leibniz notation. So dependent is our y over independent, which is our x, which is the same thing we got when we did average rates of change calculation to estimate, because we were doing the change in y over change in x, and we were able to match up those units. So let's go ahead and look at a couple problems and start to understand how these units work and how we can attribute them to different problems we're working on. Suppose that the position of a falling stone is given by s of t in meters and time t is given in seconds. Then s prime of 4 equals -7 means... So here, I want to remind you that in physics, position is often represented by the function s of t. It doesn't have to be. We could use f of x or g of t or any other representation, but the convention is to use s of t when you're talking about position. Now here, s of t is our dependent value here, our dependent variable, and that's given in meters. And time t is our independent variable, and that's given in seconds. So s of t is our dependent variable, and time is our independent variable. So when we talk about s prime of 4, the derivative at 4, the number that you plug into a function or the derivative, or really any number you plug in anywhere, is always an independent value. So it's going into the independent variable. So 4 is representative of our independent value. So our independent variable has a unit of seconds. So this 4 is in seconds. Now this -7, that's our derivative when time equals 4. So that's the rate at which our position is changing when time equals 4 seconds. So to get the units of the derivative, again, we're going to take the units of the dependent variable over the units of the independent variable. So here, that means I'm going to have meters per second. So here, once we've attributed the right units to our numbers, we can construct a statement that represents what we're looking at. So here, after the stone has fallen for 4 seconds, it's moving at a rate of -7 meters per second. So we need to make sure our sentence has the numbers paired up with the right units, and then there's lots of ways we can write that. We could also say something to the effect of, the stone is falling at -7 meters per second after it had fallen for 4 seconds. So there's not one right way to write a sentence or to talk about what it means, but the idea is that the number is paired with the right units. Then there's lots of ways you can say the same thing. So in this particular example, if delta S represents the change in position during a time interval delta t, so delta usually means change, okay? So the change in S, or the change in position during a small time interval, and we're looking at the change in time, and if the object continues to move at this velocity, we could also make a statement that the change in position is equal to -7 times the change in time, as long as the velocity is small and as long as it's not varying. So that means we can predict what the change in position is going to be by multiplying the change in time times -7, since that's the rate at which the object is falling. So in general, we can write the change in position is approximately the derivative at that certain time times the change in time for small values of t. So in general, our change in position is going to be approximately the derivative, or the rate of change at which something is falling or moving, times the change in time for small values of t. Now, what we're trying to understand is that for a small change in time, if we multiply it by the rate at which we're falling, it will help us understand the change in position, or how much it changes. We're going to use this idea later on to be able to predict what's happening at different points on a function. Now, if the derivative of a function is not changing rapidly near a point, so if it's not doing anything extreme, it's not jumping or looping or doing anything crazy, then the derivative is approximately equal to the change in the function when the independent variable is increased by 1 unit. So when we talk about what the derivative means, we're talking about what happens when we change the independent variable by 1 unit. What is the impact on the dependent variable? If we go back to our s prime of 4 equals -7, what that tells me is that if I go from 4 to 5 seconds, so 1 unit change in seconds in the independent variable, I'm expecting my position to change by -7 meters. So it will fall an additional 7 meters. So again, it's the idea of changing your independent variable by 1 unit. What sort of impact does that have on the dependent variable? That's how we interpret what the derivative is telling us. So let's go ahead and look at some examples and get used to attributing units and making meaning from our derivatives. Example 1, Part A. If S of t is the position of a moving object in feet and time t is measured in seconds, find the units of the derivative of S of t, also known as the velocity. So remember, there's 2 different ways we know now to write the derivative. So we could use Newtonian notation, which would be s prime of t, or we could use Leibnitz notation, which is the derivative of the dependent variable with respect to the independent variable. So since here s is my dependent variable and t is my independent variable, this particular derivative would be ds dt. So the units here are going to be the units of s, which we said were in feet, over the units of t, which is time, which was measured in seconds. So here, the derivative is going to have the units of feet per second. There's also an interesting relationship here that we should note. This says that if we take the derivative of position, That's called velocity. And velocity is often written with a v. So we can say s prime of t equals v of t. So that means that the units of velocity in this problem would be in feet per second. And that's also the units of the derivative of position. Part B. If the velocity, v of t, of an object has the units found in part A, then what are the units of acceleration, a of t, which is the derivative of velocity? So again, let's start with some notation. So we're looking for the derivative of velocity, which in Leibnitz notation would be dv dt here, because v is now our dependent variable. And so here, the units of v say that it's the units that we found in part A. So that's feet per second. So that's just the units of v. Our independent units are going to continue to be time. And since we're going predicated on part A, the independent units have not changed. They're still going to be in seconds. So we get feet per second divided by seconds, which is feet per second squared. So the units of acceleration, or the derivative of velocity, are going to be in feet per second squared. So something new and interesting happened here, where our dependent variable no longer had a single unit, but instead had a rate as its units. So when you have a rate, you can still do it the same way. You're taking the units of the dependent variable, whether it's a single unit or a rate, and you're dividing by the independent units. And here's a little tip. When you have a rate, whatever was in the bottom is always your independent units. So you can just copy that down in the bottom. So you're always going to end up with something squared. Now, just to be really clear about the relationship we have here, we said the derivative of velocity is acceleration. Now, just to sort of give us a glimpse into the future, I want you to notice that when we took the derivative of position, we got velocity, and the derivative of velocity was acceleration, which means that the second derivative of position is acceleration. So if we were to take the derivative 2 times on position, we would end up at acceleration. We haven't talked about the second derivative yet, but in the next section, we'll spend a lot of time talking about it. And we'll circle back to this in chapter 3, this idea about the relationships between position, velocity, and acceleration. Example 2. Use the graph below to A, estimate g prime of 20 using the tangent line, B, find the units of g prime of t. So this is similar to what we've been doing in previous sections, only now we're also concerned about what the units are of our approximation. So if we want to approximate the derivative at 20 using the tangent line, we need to draw in a tangent line that touches at 20. So I've drawn one in to the best of my ability here, and it's in orange. So what you'll notice here is that right at 20 is where we're going to touch. So right about here. And again, if I want to approximate the derivative at 20, I'm looking for the slope of the tangent line. So in order to do the slope of the tangent line, I need to find 2 points that are on the tangent line to approximate the slope. And again, I can pick any 2 points I want that it appears the tangent line is going through. However, I want to try to pick them so that my calculation is as easy as possible. So here, if I look carefully at my tangent line, it looks like it's going to go through the point 16, 0. So the left endpoint right here looks like it goes right through here. And then I'm also going to pick the point 41.5. Again, if those aren't the points you picked, that's okay too. I see the point 32, 1. That would be pretty good. 20 and maybe 0.25 would be okay points. So any 2 points on the line. Once you have the points on your line, we can approximate the derivative at 20 by doing the change in y over the change in x. So remember, our y values are the second values here. So I'm going to do 1.5 minus 0 divided by 40 minus 16. And that's going to give me 0.0625. So now that's part A. I've gotten a slope of the tangent line. It's an approximation because I'm estimating the points. It may not be perfect, but it's pretty close. And now I want to take that number and I want to give it units based on the problem here. So what I want you to notice is that in this graph, the dependent units are in kilograms. So that's what's going to be on the top. And then the independent units is in weeks. So g prime of 20, the derivative at 20, is 0.0625 kilograms per week. So whatever this is increasing by 0.0625 kilograms for every additional week that we go on. So if we went from 20 to 21 weeks, we would expect that whatever this is would gain 0.0625 kilograms. Because again, this is the idea that we're increasing the independent variable by 1 unit. So going from 20 to 21 will increase the dependent value, kilograms, by 0.0625. Example 3. The time for a chemical reaction, T in minutes, is a function of the amount of catalyst present, A, in millimeters. So T equals F of A. We want to interpret the following statements. F of 100 equals 7 and F prime of 50 equals 4. Now, it's very tempting to always turn T into time and to always make that your independent variable. But here we have to be extra careful because I want to point out that my independent variable here is A, and A is in milliliters. And it turns out in this particular example that my dependent variable is time, which is minutes. Now this is unusual. Generally when we have time, it's our independent value. So here we have to be extra careful when we're assigning units and making meaning of our statements. F of 100 equals 7 means here that the 100 is actually in milliliters, which may not be what you had initially thought. But remember that my independent variable A is what I'm plugging in. So I'm talking about what happens when I have 100 milliliters. Now 7 is going to be my time, and 7 is going to be in minutes. Notice here I'm not talking about the derivative. I'm just talking about F of 100 equals 7. So I'm talking about the time for the chemical reaction when 100 milliliters are present. So the time for the reaction is going to be 7 minutes. So when I construct a sentence, I need to make sure I'm talking about 100 milliliters and that the reaction time is 7 minutes. So I could say something like, when 100 milliliters of catalyst is present, the reaction takes 7 minutes. So again, what's important here when I make meaning is that the numbers are attributed with the right units. There's lots of ways we could write this sentence. Now let's look at part B. Now we're talking about the derivative of this function, and we're talking about f prime of 50 equals 4. So again, the 50 is going to be in milliliters, because again, that is my independent variable. So I'm talking about the reaction when I have 50 milliliters of the catalyst present. That's the point that I'm talking about in this particular problem. Now the 4 is the derivative. So here, because I'm doing the derivative, I can use Leibnitz notation to think about what the units are going to be. So the derivative of capital T over dA with respect to A. So the derivative of time with respect to milliliters. So here, my T is in minutes, and my independent variable is in milliliters. So the units of 4 are minutes per milliliter. So what does that mean? So that means when I have 50 milliliters of this catalyst, that my reaction is speeding up by 4 minutes per milliliter for every additional milliliter of catalyst that I add. So my sentence could look something like this. When 50 milliliters of catalyst are present, the reaction is speeding up by 4 minutes per milliliter. So what that means is if I were to go from 50 milliliters of catalyst to 51 liters of catalyst, my reaction would speed up by 4 minutes. So by changing the independent variable by 1, it would change the dependent variable by 4. This idea also works in the other direction. So I would know that if I reduced the milliliters of catalyst from 50 to 49, it would then slow down the reaction by 4 minutes because I'd be moving backwards in time. But again, the idea is that we want to take the numbers and attribute the correct units so that we can make meaning and talk about what's happening. And again, just as a reminder, time is not always the independent units. Most of the time it is, but occasionally, in an example like this, we get time as our dependent units. Example 4. The amount of medicine in milligrams found in the bloodstream, C of t, is a function of time t in minutes after taking the drug. We want to interpret the statement C of 35 equals 90. So inside of our function is our independent units, where we said was time in minutes. So this is 35 minutes. And C of t is in milligrams. So this 90 is in milligrams. So I would interpret this statement as 35 minutes after taking some medicine, 90 milligrams of that medicine can be found in the bloodstream. So again, the 35 needs to go with minutes and the 90 needs to go with milligrams. Part B, write the derivative of this function using Leibnitz notation. So Leibniz notation says we're going to have the derivative of the dependent variable with respect to the independent variable. So we're going to have dc dt. That's going to help us in part C figure out what the units are going to be. So part C says interpret the statement C prime of 15 equals 7. So remember, the number that we're plugging in is always your independent variable here. So this is going to be in minutes. And the units of our derivative are going to be the units of C over the units of T. So the units of C are in milligrams, and the units of time are in minutes. So the units of 7 are in milligrams per minute. So the statement C prime of 15 says to me that 15 minutes after I've taken some sort of medicine, the amount of medicine in my blood is increasing at 7 milligrams per minute. So what that also tells me is that if I were to go from 15 minutes to 16 minutes, I would expect the amount of medicine in my bloodstream to increase by 7 milligrams. So again, 1 unit increase in the independent variable has a 7 unit increase in the dependent variable according to this derivative.